So, one quick question, because you will know that this is a marketing talk, right? I'm going to talk about products and prices and everything, right? This is what you come here for. No, I'm kidding, of course. Of course not. Now we're going to talk about internals. And one thing I want to convey in this talk is precisely, how I would say a big project. This is a project that is around 150,000 lines of code. I mean, it's not super big. There are a million lines of code projects out there, but it is quite complex. And it's been developed for almost 3 years. So, I mean, it's not a toy project. And what I'm going to talk about today is several of the issues that we encountered and how we solved them, both from the perspective of the technologies that we used and also from the perspective of the techniques that we use. Most of them are, of course, database related, but you don't need to have a database background, even if you have, because I'm just going to show Java code also, and this is going to apply to mostly any project. So this is basically the learning experience that we've got from developing this medium-sized to big project, I would say. And hopefully that will be interesting for you, and you can apply on your own projects these learnings that we have. Just before starting, a couple of quick questions. How many of you do you know what ToroDB is? All right, a few hands over there. Don't worry, I'm going to explain what it is, just to give some context. It is open source, right? So you can go and check the source code anytime. What else? The second question: how many of you do use MongoDB? Oh wow! And what about Postgres? Oh, roughly the same number. So you're on the right place. Because if anything, what ToroDB does, and let me start with a quick introduction here, is to communicate both worlds, to be able to take data from the NoSQL world and put it into the SQL world. Basically, it takes any document, any collection, any database that you have on MongoDB, and bring it automatically to a relational database like Postgres. You actually don't need to do anything. You don't need to create tables. You don't need to define the schema. You don't need, just give it an empty database, and it will be full of data, all created in relational tables. Like let's say, if automatically someone designed the schema of the data for you. So it's going to take unstructured data, NoSQL data, and turn it into structured data, into relational data, purely relational. So the first question could be, why the heck do you want to do that, right? I mean, if you pick NoSQL, you probably don't want SQL. Any idea why this might be interesting? Data warehousing, absolutely. So one of the main problems that NoSQL in general faces is because of the fact that data is unstructured. Performing analytics, performing computations on data, it's very hard because you need to reparse everything, to analyze everything. You may be analyzing many documents which might not contain the information you're referring to. So because all of, just think if you take a pile of pieces of Lego and they're all mixed up, and now I say, hey, give me all the yellow pieces. Well, to look through the whole thing to get back the yellow pieces, right? However, if you would have designed this in a relational schema, you will probably have the yellow pieces on one side, the red ones on the other one, the green ones here, and it's very easy to pick. Of course, this is a very, very poor oversimplification, but the fact is that with a relational schema, data is structured in a way that is much more easier and much more performant to perform operations like data warehousing, data analytics. Typically, we've seen, and the benchmarks are published on our blog site, we've seen improvements between 1 and even 2 orders of magnitude faster queries for analytical types of queries when comparing basically MongoDB and ToroDB. So, but this talk is not about what ToroDB is, what it's going to do for, and what the advantages are. There's actually many talks of that in the internet if you want, but I'm going to talk today is about internals. So just before diving into the internals, let me just do a very quick demo so you can get a feeling of what ToroDB is. So basically, ToroDB it's going to connect to MongoDB cluster as a secondary node. And as soon as it gets connected, it's going to start replicating all the data. First of all, doing an initial sync, and then it's going to perform a live replication from MongoDB to Postgres. Table creation is automatic, data design is automatic, and just connect ToroDB to MongoDB, it will start replicating, you'll have all the data in a relational way. Let me demo this first before we dive into the problems and how it's laid out internally. So hope that you can read this font size good enough. It's okay? All right. So I have ToroDB, sorry about that. Here, just recently downloaded from the website. Yeah, here it is. So this is the source, this is the compile code, this is Java classes. Let me install this. So I'm just going to start from scratch, just to simulate what you might also want to do. This is, needless to say, programming Java. So this creates some folder here. ToroDB, if you follow some conventions, you don't need configuration. Just you follow these conventions, you can start without the config file. You can also create a config file in YAML or JSON. And I'm going to follow these conventions to simplify this part a bit. So it's going to connect to Postgres. So in Postgres, I'm just going to follow these conventions, and I'm going to create a database called ToroD, owned by a user called ToroDB. And because I follow all these conventions, right now I can start ToroDB. There's a Mongo server here running. It's on replica mode. I mean, it's cluster mode, so we can replicate from it. And I'm just going to start. I'm going to run this inside the screen. So I'm going to start ToroDB. If all goes well, it should start right now. It boots. There's a bunch of logs out there. And at some point, we'll see that it connects to the replica. Okay, it's now reading from Ushuaia on this port. So, and it already started on secondary mode, which means that already replicated the data. There's almost no data there. And right now it's replicating this data. So let's open a new window here. Let's connect to the database that we just created. And as you can see here, there's some schemas automatically created. This was an empty database I just created before, right? And the start ToroDB, see that there's a test schema, and then ToroDB and the /ToroDB, that's for metadata. Let's do something with this. So let's go to MongoDB. Let's create a database called JokerConf, or Joker for short. And let's insert some document here. So let's say db.test.insert, and let's insert document. Okay, and now let's go back to Postgres. There's now a schema called Joker, as you can see here, right? And if we list the tables here, or actually let's just select Joker, there's a table called test and contains a field somehow called A with a value here. So this is more or less how it works. You know, we are now connected to MongoDB, replicates all the data live, transforms into relational tables, and we have the data into Postgres. Let's do a little bit more advanced example. So let me just change the record here. There's a JSON document. Okay, I'm gonna insert this JSON document, you know, about some conferences. So just let's again use the database Joker, and let's say db Joker, insert, and then let's insert this document. All right, let's go back to Postgres. List the schemas. Here we have Joker. List the tables there. And now we can see here that there's more tables that have been automatically created. There's Joker address, there's Joker address, Joker conferences talks. This looks a little bit like my data before in the document. And indeed, if I go and select all this data, I can see that this is the root table, Alvaro Hernandez, that's my name. There's also this address, conferences, and the conferences something else, talks. So all the data is here. As you see, you just inserted this into MongoDB, and it replicated live, created it into the relational tables, and here we have the data. We'll discuss how this is useful. So in order to do that, let's just import a bulk of documents. So I have a real collection here. Actually, you don't have the collection here, but let's do a Mongo import, creating a new database, which is going to call Joker2 collection, also Joker, not delicious, which is I'm going to import the collection of bookmarks from public dataset called delicious, and the dataset is here. Yeah, so let's search 10,000 documents. All right, this worked, and now let's connect to Postgres, which is here. And there's Joker2. We see that there are some tables here, and for example, Joker2, delicious. So this should return 10,000 documents, that's correct. So why we wouldn't want to do that? If we go to MongoDB, and we connect to Joker2, and we say db.joker delicious find, this is what we get. Can you see? It's amazing. Right? Now perform analytics on this. Tell me something about the data. It's a bit difficult. However, if we go to relational schema, well, okay. That will help. Probably. The font is too big. Okay, that's more clear. Right, so we can see the data is now perfectly structured. And this is like the root data. If we look at the bookmarks, for example, or the links, right? So this is a document with the links. Everything is well organized. So this is, the advantages of the system. I don't want to talk about this more because I want to look at the internals, how this works and the advantages of disadvantages. Just I would like to open a round of questions. If there are any questions before I proceed with the internals about the working or the why, or all good? Yep, okay. So, a little bit about myself. I am both a DBA and a software programmer in Java, so I kind of sit between both worlds. And I am the founder of the company behind ToroDB, which is called 8K Data, and ToroDB project itself. I typically speak at Postgres conferences, some also Java conferences, and you can find me here on Twitter and or here, just feel free to ping me. Okay, so we have explained already what ToroDB is, so I'm just gonna dive into this anymore. Let's look at the architecture. From a high-level perspective, ToroDB is layered into several components, right? At the topmost, there's two entry points. One is called MongoWP, and that's wire protocol, and that's where we parse and speak the MongoDB protocol. This we do at the byte level. It is a TCP connection. We use Netty, the async IO framework for this, to implement in this. It is actually a separate project that ToroDB declares as a dependency, because we wanted to make it easy for others to create MongoDB-like servers. So if you want to emulate a MongoDB server, you can go and use MongoWP as a dependency on your project, and you can create a MongoDB server. It is, of course, non-trivial, but this is something you can do. Actually, as of today, it's a little bit tied to what ToroDB requires, but at least the idea is there. After all, it's also open source, so you can go and fork it. There's also another entry point for the replication, because the replication actually is a bit different from the rest of the MongoDB protocol, so that's a separate entry point. Then there is a MongoDB layer, WP layer, where we actually parse the commands and all basically the commands that are sent over the MongoDB protocol. MongoDB protocol is very simple in terms of messages, basically has right now 4 messages. But one of them is execute command. So it's like a backdoor where you can do almost anything. There's an intermediate layer that we call here Document-to-Relational. And this layer serves what's that? serves two purposes. One is to provide an abstraction layer over the MongoDB protocol. We want this architecture to be able to support other incoming NoSQL databases, not only MongoDB. So in the future, we want to implement, like, for example, Couchbase. So we have an intermediate representation here that is abstract. It is called Kiwi document, which abstracts away the fact that it's a MongoDB document. So we take conversion from MongoDB document to an abstract Kiwi document, and from there we perform the transformation to relational, which is the algorithm, the main algorithm of ToroDB. So in the future, if we want to implement Couchbase, we can transform from Couchbase to Kiwi document and apply the same algorithm here, and everything will work as is, with a few caveats, but basically that's the point. Then there's the executor. Once we have transformed this document, this actually batches, it operates on batches, we're going to see batches of documents into a set of relational structures. We need an executor to basically write those to the backend. The executor holds a cache. This cache is a cache not about data, but about the metadata, basically about the tables and the columns and the data types that the database has. Upon restart, this will be read from disk. This cache is very easy to maintain because we designed it on purpose to be append only. We, across ToroDB, we never, unless you perform like a drop database operation, we don't rename columns, we don't drop columns, we just add new tables, add new columns. We never change the types. So basically data is immutable append only. So this cache is easy to handle because there's no invalidation. And then there's a common layer for the backend. The same way we want to have independence in the incoming protocol and support all the incoming NoSQL data from all the NoSQL databases, we also want to have several backends, and actually we have two. We have a Postgres backend and a MySQL backend. So there's also a common layer across them. This is not just saying we're going to use JDBC. And of course we use JDBC, but it's not enough. There's many significant differences between the backends and generalizations we need to make about them, like how they handle the DDL, how they handle locking, and some data types how need to be transformed. So there's a bit of magic happening there. We're going to see part of it. So how the document is transformed into tables, it's actually easier than it looks like. Basically, if we have a document like this, every field is going to be mapped to a different column of the given type, so name, surname, username, address. Whenever there's an embedded document, if you think about it, an embedded document, it is a one-to-one relationship in the relational world. So how do we represent the one-to-one relationship? It could be collapsed, but in this case, we just externalize to a separate table, and it becomes a separate table. In this case, it's an embedded document, right? City and string. And then there's arrays. Arrays, collections, are actually resembling a one-to-n relationship on a relational schema. So we're just going to map also to an external table with potentially several entries. There's only one entry in this example, but it could be several entries. And this could be also documents, embedded documents, which will go to different tables. Recursively, it can support any structure, any JSON documents. There's no limitations. There's not even limits. MongoDB has a limit of 100 levels of nested documents. We don't have such a limit. I don't know about performance, but there's no limit. Once this is done, this needs to be written to tables. And basically, everything that you see here is written as a table as is. The field maps to a column, and the fields on the same level belong to the same table. However, we need to add a couple of internal fields. I don't know if you can see them well, but I'll explain to you. Or actually, I'll show probably in the code. It's going to be even easier. So let's see. We had here. We'll look at the first example that we inserted here. Yeah. So we have the name, the surname. First of all, we add a suffix that is basically a placeholder for the data type. So this way we support conflicting data types. If you have a field name, which is an integer in one document and a string on another one, we'll have name underscore s, name underscore I, and one of each will be null in every case. So we support data type conflicts very easily. There's also metadata tables that reflect this. This is an internal field of MongoDB, the underscore ID, which is like an UID, always comes with MongoDB. And then we have this internal field called DID, which stands for document ID. You can think of this as the internal ID or primary key. If we look at the nested document here, like address, here we see more fields, like the DID is the same because it belongs to the same document, so all pieces of the same document will always have the same DID. That's why we can retrieve them back together. Then there is the RID. The RID is used in arrays to indicate the position in the array. Is the row ID, which is used when there is more than one entry. If there is a mapping that contains more than one entry, that will be used to distinguish the position in the row, so it's the row ID, and the sec is the one that I was telling that explains the position within the array. If we look at address, conferences, here we have an example because there's two elements here, so we have different row IDs, and if there's some level of nestedness, we might also need an extra field which is called the PID, which stands for parent ID, which basically goes back to the previous table and say which is a parent ID of this row. So with all these internal columns, which could be null at some point, the DID, RID, PID, and sec, we are able to fully reconstruct the document back together. And this is basically what it explains here. So don't want to use more time here. There's a few metadata tables, like docpart. Docpart is basically a metadata table which contains the tables, which resemble the document shapes that we have created, and contains this. The more important part here is the table reference, which is like the path of these documents. And then the fields are columns, right? And they represent the columns that appear and the name of the identifier, the type that it has, and so forth. Again, this is of course all created automatically, so you can use this information to make your queries dynamic or automatic from this information. And the way we read back the document is very simple. You just collect all the tables which are referenced here that have the same document ID, and we build the document bottom up. So we start reading from the small from parts like this, and then we start building like the nested parts, and then we start building back the hierarchy until we get to the root document. All right, so this is more or less how it works. Let's now look a little bit about the technology and some problems that we face that are interesting to mention. So first of all, the replication pipeline. As I have mentioned, ToroDB replicates the data from MongoDB. And if you think about this replication process, this is very stream-oriented, right? This resembles clearly a pipeline of operations that we need to perform on a stream of data. And here, there are some concepts that are critical for us. For example, the back pressure. If we don't apply properly back pressure, we can completely overload ToroDB with data. If, for example, MongoDB would be faster as a producer, we will crash ToroDB. During development, we also experienced problems with high memory pressure because a lot of object creation. So again, we needed to apply some back pressure. And there's also the need to apply many transformations, as you can see here. And the logic of all these transformations, of all this process is non-trivial. So because of all these requisites that we want to apply back pressure, that we want to apply complex operations at each stage, that the logic of connecting all these operations is non-trivial, and also the fact that performance is critical, and needless to say, we need to be as much concurrent as possible. We want to execute most of the operations that we can asynchronously. So for all these reasons, we decided to go with Akka Streams as a technology to support this underlying pipeline of the replication, because it allowed us to easily construct all these complex operations, and you're going to see more or less how it works. So we start from the off-heap buffer, so all the changes that are streamed from MongoDB by the replication layer that we wrote are taken to an off-heap buffer to avoid object creation in the first place. From there, we apply some filters that the user can specify, hey, I don't want to replicate this column or this collection or this database, so we can filter some things. We also then check for unsupported operations, because not all the operations that MongoDB uses on the replication protocol are used. For example, a ToroDB node cannot be promoted as a master. So there are some unsupported operations. Then I'm going to talk about this in more detail. We perform a grouping of operations to basically, we don't execute the changes that, from the replication channel, you basically get either an insert, a delete, or an update. That's basically what you get. And we don't apply the operations on a one-by-one basis as soon as we can. We actually transform them, break them into pieces, group them together. There's some complex logic I'm going to talk about today, and that is performed here. And then finally, we execute that. And once everything is executed, we feed it to a part of the pipeline which collects metrics, so we can know how the system is working. So there's also a metric system embedded into this. And basically, this is 20 lines of code with Akka Streams. Of course, this is not completely true, because some parts here involve much more complexity than it looks like, right? But basically, if you're unfamiliar with Akka Streams, you basically create a description of what is your pipeline. That's called a runnable graph. And it's going to return, it's going to provide some placeholders for yourself to operate this. And there's a source of data, which in this case comes from the fetcher, which fetches the changes from the MongoDB replication. You see some async calls, which means the points at which basically there's going to be an async barrier. So the groups that are between these async blocks are going to be operated synchronously. So all this part is synchronous, so like all these 4 lines are synchronous, but the whole block is asynchronous on itself. And Akka will take care of how to dispatch this between all the threads, or the actors, technically speaking, which is very good, because it was also very hard for us at the first implementations to control the number of threads. That it's very easy to create thousands of threads, or just use 2, and then it's not really easy to manage that part. So this was also very helpful. And we can also implement parts which are very, very useful on Akka Streams, like kill switches, which is basically a point at which you can control externally and say, hey, stop this pipeline because there's been an error, we need to restart, we need to do something else. So you can get a kill switch and stop the operation at some point. And actually, the meat happens here. Those are the analyzed elements, and we kind of basically iterate through all the batches that we have, and we execute them on the executor, which returns the same elements for the metrics to be collected. I'm not going to get into the deep details of this, but I hope that you can get an idea of such a possibly complex pipeline, which involves really complex scenarios, can be summarized in just a few lines of code, which are kind of easy to read. DDL changes. So this is an important part that we faced. You might think that because there's JDBC, yeah, this is trivial, right? We just use JDBC and run the queries, and it works, and it abstracts away the databases, and we're all happy. However, this is not the reality. Unfortunately, some databases operate differently than others. And even so, because what we're doing things will be a little bit unconventional, because we are creating dynamically tables and columns and so forth, things are not as easy as it looked like. So, because we are doing this in a stream processing manner, just let's think that there's some data. And at some point, some data contains a new field, a field that we haven't seen before. If this happens, we need to create a new column. This is done automatically, but we need to do that. Because we are on a stream manner, these changes can mix. So we can have at some point just data, like with something which in turn will become an insert. And then it comes an insert of a new field, and then we need to create a new column. So we'll do an alter table at column blah. Which means we're gonna be mixing DML commands, insert, update, delete, with DDL commands, creating a new column. So we're mixing DDL and DML commands. We first implemented this as a Postgres backend, and everything worked fine, because you know what? Postgres has transactional DDL. You can do begin, create table, drop table, create whatever, roll back, and everything will disappear. It's atomic. However, you go to other databases like MySQL, and you start inserting data, and you say alter table add whatever, and transaction automatically commits before the DDL command. So atomicity is violated. And this is a big problem. Same happens in Oracle. So what do we do with this? The first obvious idea, it's to say, okay, then we will execute the DDL on a separate transaction. We have probably one thread that will, or a group of threads that will execute DDL commands, and then we have the threads that will execute the DML commands, right? There are a few requisites for this. The first one is that the backends need to provide read-committed isolation mode for the DDL commands. That's fine because almost all of them seem to have this. But there could be deadlocks. So basically, because any DML command inserting typically, if it needs to create a column, it needs to wait on DDL. So impose a rule that any DML command must wait on any pending DDL command to be executed. However, if you're reading a table, because you're executing a transaction which involves reading something and then modifying something. This is, for example, happens on a updates or delete scenario, where you look for the record first and then you update it. You read it, so you acquire a read lock. Then you realize you need to create something, and this some DDL. So you call the DDL manager, and the DDL manager tries to acquire an exclusive lock because it requires an exclusive lock. And it can't because there is already a read lock. So it waits. But then the initial read transaction tries to continue, and because it cannot go over the DDL command, it cannot continue. So there's a very simple automatic deadlock. So this doesn't work as is. And actually, the solution that we came up with after a lot of debate and testing and studying several solutions is to basically stop the world, to say it in a very simple manner, whenever there's a DDL command. So what we do is that even though we're operating in a stream, because we also computed the possibility of generate a whole batch of operations, analyzing which ones are the DDL, put them at the beginning, and execute them before the batch. But this actually was slowing down significantly the performance. We were operating on large batches, typically on 1,000 elements per batch. And typically the database is a bit slower than our processing in Java land, much slower. So if we wait until the end of the batch to look if there is any DDL operation, we're wasting a lot of resources. A lot of rows that could have been already inserted are waiting. So rather than doing that, because after all, DDL operations are quite infrequent, it's just adding new fields or so forth, that what we do is whenever we start executing, we start inserting data, and if we find a DDL operation, then we actually roll back the transaction, discard the data that we just inserted, take the DDL operation, stop the world, execute it, and then retry the original transaction. Because right now, the original transaction, the DDL will not be executed, because before executing a DDL, we go to the cache, and the cache, this column already exists, then this transaction will proceed. It, of course, it could be more effectively implemented, like, for example, if the operations are not interleaved, like, for example, you're talking about different databases, we don't need to stop the whole world, but really, DDL operations are infrequent. Happen more at the beginning, when you start with an empty database, but otherwise, this works. Another solution we didn't do could be to create a lazy system, where basically a client could request something like drop something, and then there's modifications on the cache, the metadata, and then you can continue, and this kind of drop operations are performed later. But it's very risky. There could be race conditions. When you drop something, someone recreates it, and it's non-trivial. So we prefer to go this route, and it seems to work quite well. As I was saying, there's some grouping of operations. So again, we're replicating CUD, create, update, delete, and this is what we have in our stream. And what we want to do is to use parallel appliers. If we use a single thread, performance is not going to be really good. So what we do is to try to separate things in several appliers. How do we do that? Actually, because everything is identified on MongoDB with _ID, the triple database collection _ID, that is a grouping indicator. So we group documents, operations for this 3 tuple, the database collection ID and _ID, and those operations we execute on the same thread, in the same order. However, operations that go on a different database or collection or ID or any of those, they can go to a different applier because they are not related, because in MongoDB there's no foreign keys, there's no relations. So we can do this very easily. And we can create as many parallel appliers as we want, and this is a very easy technique, and it really improves performance. But even more, these operations that we call CUD, create, update, delete, are internally not atomic on a database like ToroDB. Basically, insert is atomic, create is atomic. However, all other operations like update, delete, or upsert, they require to look for the records first, which you want to modify, to update, to delete, and then perform these changes and then delete or whatever. So we can break these operations down into a set of sub-operations, like you can see here. So basically, create could be an I insert if there is no upsert, or it could be a fetch the document, delete the document, modify the document, and insert the document if upsert is true. The same with update, which is fetch, delete, modify, and insert, and delete, which is a D. So these high-level operations can be broken down into smaller pieces. And actually, these smaller pieces, we also group them somehow, following an algorithm, then we can group them and parallelize them further. And it's basically quite simple. For operations that belong to the same document, we can perform first all the fetches. So for example, if you're modifying in a batch, think of a batch of 1,000 documents, you're performing a lot of deletions, they need to look for many documents. You don't want to do a query like select this where ID equals X, select where ID equals Y. You prefer to say select the ID for these documents where _ID is in X, Y, Z. You execute a single query. So by grouping all the fetches first, then we can do all the DMN operations, and finally all the I operations. And we created invariant tables to make sure that this actually works, and it does. So we improve performance together with this breaking down in smaller operations, as well as the applying in parallel. We can improve performance significantly. And of course, this is more or less easy to integrate with Akka Streams. Again, not a lot of code to represent all this. We created some classes, which is like, for example, the batch flow, which has a timeout, in order to wait a bit to fill the batch, but not too much. And basically, the analysis, this is the part that breaks down this into pieces and returns the analyzer stream, which is sub-operations. But other than this, this is just a new flow with some filtering and a mapping elements. Quite nicely fits in this Akka Stream pipeline. More things. I mentioned at the beginning, we use Netty very intensively for the network protocol part, for the MongoWP, but we also use it for keeping as much data as possible off-heap for as much time as possible. So basically, when we receive data, Netty can use off-heap buffers, and we do that. And then when we need to start using it, they're actually moved to the heap. And we keep them to the end as is. And actually, we basically try to deserialize, to convert these bytes into strings only for the strings needed, only when needed. And this is actually quite simple. So there's a class that we used for this, which is called Netty Bison string. Bison is a binary serialization format of MongoDB. And we basically, this method here, the get string, which takes a byte buffer, which is the Netty's representation of an array of bytes. We just convert the part to a string, but only when we really need the value. So, the naive approach would be to, to parse every message you received on the protocol and convert everything to a POJO, and give the POJO to all the layers. But this is very, very ineffective, and we suffered a lot of memory pressure for a lot of extra string creation on the first stages of the development, which of course use that more naive approach. Needless to say here, what this receives is not a whole byte buff. The byte buff can also be a sliced byte buff. So you say, this is like the whole document, the message you receive from Mongo, and you pass it only this slice, which is in turn a byte buff. So this represents the whole string. We also use some other off-heap buffers. Remember, I was talking about how critical back pressure is for us. And typically, MongoDB can be very, very fast in insertion, and we're a bit slower. Not very much, actually. It's like 1 point something. But if there's a spike of load, we might need to hold down MongoDB, pushing us data a little bit. However, we can do this at the protocol level and just not request more data from MongoDB. But then the problem is that MongoDB doesn't hold the changes information for a long time if configured like that. It has like a window under which it will maintain the changes happen to the database. And if you don't read quickly enough and this window is over, you lose the synchronization with MongoDB, and then we need to start from scratch to recover the database. We need to drop everything and copy everything over and then synchronize with this sliding window of changes. So because we don't want to do that, we decided to implement an off-heap buffer based on Chronicle queue. I don't know if you're, just curiosity, how many of you are familiar with Chronicle queue or Chronicle? General, okay, a few of you. So we use it as an off-heap buffer, so everything is a queue, right? It's off-heap, and just it's a circular queue, has a limited size, and can also persist to disk. And this is quite handy because if, for example, even if we crash the instance, we already fetched a lot of data from MongoDB, and we can process that and not to lose the synchronization window with MongoDB. To use Chronicle queue, it's quite simple. Just basically instantiate it, setting up the, you get an off-heap configuration, you set up a path, which is the path where you're going to be persisting the data, specify some number of maximum files, and you basically use a builder pattern to get Chronicle keys, not rocket science. However, we of course wanted to integrate it with Akka Streams. So we created a class that allows us to basically integrate this Chronicle queue very easily with the rest of the flows. So it's basically a flow, and we can create it, we can integrate it very easily. So strings. Please raise your hand if you haven't had problem with too many strings created on a program. Okay, that means all of, okay, you haven't. Lucky you, buy a lottery ticket today. Yeah, we definitely suffer this. Just think of what JSON documents are. Strings, right? And some of them actually repeat a lot, the keys. Even though this theory of a schema length means that you can throw anything, actually the reality is that the variety is small, and there's few keys and few different document types. So there's a lot of strings. Actually, most data are strings, but also there's the keys that are repeating all the time. So how can we optimize this and avoid string creation? Interning. That's what it says? Yeah, okay. Actually, yes, of course. So we do string intern, right? Vladimir was laughing like crazy. Of course not. That I was going to say one word, but I'll just say that it works slowly. So now we needed to do something else, and for this we basically use Guava's interners for the strings, which work significantly better. And one of the significant differences is that, first of all, we actually implemented a string pool which uses weak references. This is actually done by Guava, which basically allows unused keys to be garbage collected. So we don't have a cache of gigabytes of which can happen with a string intern. And we also select based on a policy based on a policy which strings we want to intern and which ones we don't. Basically, the very small ones we don't, and because it doesn't pay us off, and the big ones we definitely don't. Although everything else is more or less, it also looks a little bit about memory consumption, but basically that's what the policy does. So this is pretty simple, just use this technology and worked really, really well for us. At one point, we were having problems with out-of-memory errors and consuming few gigabytes of RAM for basic operations, and right now for the same operations it runs under 300 megabytes of RAM. So it's really, really, really good. A bit about sharding. MongoDB has sharding. You can distribute data into several shards, and we also wanted to support this. However, because relational databases are really good at managing large amounts of data, whereas NoSQL databases are actually not that good if you don't use sharding. We've talked with a lot of customers and users who said, whenever our MongoDB database grows over 1 terabyte of data, we just drop it and start from scratch, because otherwise it becomes unmanageable. Or they shard, of course. However, we can shard on the same database, on the same backend, but we separate in different collections. So data goes from all shards into different collections. This has its own problems per se, because the recovery state of each shard can be different. We can lose sync on one, but not on the other one. So we need to manage that differently. There's also some other issues, like for example, if there's data moved from one shard to the other one, this is data migration. That's something that MongoDB does. Basically, you get a lot of deletions and a lot of insertions, and we need to handle this with care, because otherwise, if you don't recognize that these are related operations, you might get incorrect results. So there's a few issues here. And also when you add a new shard, there's some problems that you need to consider. But the reason I'm talking here about sharding is because of the way we decided to implement this at the programming level. So basically, for getting into that, we use juice for injection, for dependency injection within all the program. And at the beginning, we supported replicating from one source. And everything worked fine. We perform all the injections. Actually, ToroDB is composed of many internal components, and you require a lot of injection dependencies, but everything worked fine until we decided to implement sharding. Because now we need several instances of the replication module. And in juice, it's meant to inject a singleton. That is actually the principle of dependency injection. And we didn't want singletons in this case. So there was some magic to be done. Apart from this, and before showing the juice code, basically, because of the operations are happening on different shards, we can perform them on any order. So this is another point of parallelization, as long as they are not related, like data migrations that I mentioned before. So when related operations are happening, there's other related operations. For example, if the user creates an index, that index gets pushed down to all the shards, because it creates the same index in all the shards. And we need to do the same thing. So first of all, in order to understand dependency between operations, we cannot look at the clock. And probably you all know this already, right? You cannot rely on a distributed clock, because they can be different values. So we had to look, in order to understand these related operations, we had to look indirectly to some things that could indicate us, what are operations that are a boundary, a synchronization boundary. Like actually the ones that I mentioned. First one is when documents migrated from one document to another one, from one shard to another one, because we see that the same ID on one place is deleted, another one is inserted. And that, of course, you can see that that's a document migration, and you understand that those were executed at the same logical time. The other one is also the other one I mentioned, like creating an index. If you create an index, the operation will push down to all the shards, and you'll receive in all the shards a create index operation with the same name, with the same definition. So then that's also like a synchronization barrier. So other than that, everything can work in parallel, except for these points where we look for these synchronization barriers and serialize those. Actually, not serialize, but wait on the barriers. And as I was referring to about the injection, because of this injection to avoid injecting the same singleton instance, we consider two approaches. The first one is to use a facility of juice, which is called scopes. And in theory, this could be good and probably could work, but we decided not to take this route, because the scope, basically, you say, this injector is going to inject this kind of objects within this scope, right? But if you make an error, if there's a bug, it will not complain. It will just inject the same instance, and you don't want that to happen, right? So this is very risky. Just a single mistake will silently give you the wrong instance injected. So we didn't want to do that. And so the option is to use several injectors. So we use different injectors. Now, this also comes with its own problems, and very, very quickly, the problems with these injectors is basically it's easy to break the abstraction because it makes so easy to inject anything from any point that I need this class. Okay, right. So you inject it in whatever piece of code, and you can very easily create circular dependencies, or you can break the abstractions. You can inject something from some other place that it shouldn't. Like for example, we were trying to optimize the startup part, and we want to perform the backends at the beginning and then the rest of the modules, but because the backend needs some operations from other modules, they were declaring dependencies in the wrong order. All right, how to do this with Juice is very easy. You just can create a bundle class and inject this bundle class. We actually use here a combination of Juice bundles and Guava services. All the components of ToroDB that operate as independently, they are presented as a Guava service. So these are methods to tear down the Guava service. But we also expose an external interface to every bundle. So you explicitly declare which are your exposed interfaces. So basically, every bundle is like a service, has its own life cycle, and also exposes which functionality it exposes. I know this sounds a lot like modularity in Java 9, but it's not that big topic. It's just something a little bit more simple. And last but not least, I want to finish this and open some questions. We did an integration of JUnit 5 and Docker. The reason is that there's a talk in parallel about this, so you can also see the videos. But this is something we developed on our own, and the idea is that we need to test this very carefully and to test these scenarios with, this shard is falling down, this is crashing, this is going very fast, this is going very slow, we need the Postgres, we need the Mongo, we need whatever, and complex scenarios with many machines, and it was very, very hard to orchestrate. So we decided to integrate Docker into Java. So from our source code, from Maven, you actually will fire a lot of Dockers and tear them down and crash them and open it and initialize with MongoDBs, with replication, with many scenarios. And we actually integrated them directly in Maven. If you like this idea, this is a separate project, which is called Testing Tools, which we have in ToroDB. It's also open source, so you can go and use it. And it's very simple. Within our own test, we just this annotation require Postgres, and you specify also the version of Postgres that you want, and you have a Postgres server, which is a Docker image with Postgres running and so forth, and then you can run your own tests. So it's pretty cool. And we also, last but not least, we also used the new facility of Test Factory in JUnit 5 to generate dynamic tests, because we also need to simulate many configurations of the testing that requires a lot of complex logic, which you cannot express statically. So with this functionality of JUnit 5, you can generate dynamic tests. That's basically it. There's a few minutes left, I guess, for questions, so feel free. Спасибо.
Вопросы?
Thanks for the talk. Actually, I have two questions. As I understand, ToroDB works near real time, but what about initial synchronization? And how do you define that initial synchronization is complete? You can start stream data. And the second question is about monitoring. How can we understand that data is consistent between the databases?
Okay, both are really good questions. The first one is any kind of replication based on systems like this, which is basically based on event sourcing, performs two stages: the initial synchronization stage and the deltas, or the changes. Theoretically, database under this assumption, when you connect to database and perform this initial change, initial state, the database is frozen. On a relational database, you basically require a repeatable read isolation mode or a snapshot isolation mode, and then the database is frozen to you. You just pick all the data, and then you tell the database, now start streaming changes since the time I took this snapshot. MongoDB things are a little bit different because MongoDB and consistency are not totally implemented. And actually, the logic is quite complex. You basically read all data from all tables while collecting the differences, the changes at the same time. You apply the changes, like you go again and do another way around. And there's actually a third one. And we were reading the MongoDB source code and trying to understand why they did that 3 times. But they didn't, so we did. They probably understand the reasons, but we work exactly the same way as MongoDB does. So if they are correct, our implementation is basically translation from C++ to Java as the same algorithm. So even though they are not strictly consistent, it works the same way. So I believe it is okay. And as for the consistency between the databases, I mean the MongoDB, and I guess that you asked that the relational database Postgres, it is ensured because in this case it's warranted by the replication protocol that all changes are sent in a total order. So within a sort, different shards they are not, but within a given shard, the order is totally ordered. So you're warranted that you could be eventually consistent in the sense that you may not have replicated all the data that you can find on the master in the MongoDB instance, but what it's replicated has been replicated in the correct order.